Hello, hello, and welcome back. In this video, we are discussing equations of planes. What we need to start with first is what exactly is a plane. So, of course, we have a mental picture of a plane in our heads, but we have to go a little bit further to actually come up with a good working definition for a plane. So, what really defines a plane is a sort of orientation of the plane, a normal vector to the plane, so something that's perpendicular to the plane, and then a point in the plane. Then we can define the plane to be the set of all of those points P, such that the point in the plane, P naught, that we've sort of decided on, the points, so that any point in the plane, P naught P, is orthogonal to that normal vector. All right, so that's a little bit of technical language there. Let me jump real quick to an example in the text, figure in the e-text, just to kind of illustrate this. So here we have a plane that's defined. We have our normal vector n and a arbitrary point that or rather a specific point in the plane. So this plane is going to go through the point P naught, and the vector n is going to be normal to that one. So here I have it set up where my normal vector looks like 0, 0, 1. So our normal vector here is k, and as you can see, it's pointing up. It's doing exactly what k does. And then I have my point P naught, which is, where's P naught? P naught's right here. So what I do to form the plane is I take all those vectors that emanate from P naught, have initial point P naught, and are perpendicular or normal to the plane. So that's all of these vectors here. Notice that it's parallel to the xy plane because I'm dealing with the normal vector k, which is also a normal vector for the xy plane. So let's just see what happens when I change the vector n around a little bit. Let's give it some x component. So now I've tilted the plane towards the x direction. My normal vector is pointing into the positive x direction as well as the positive z direction. So it's pointing up like that at a 45-degree angle. And now my plane, still going through the point P naught, I still have that same point in the plane. And again, I take all the vectors, all the points, such that P naught P is orthogonal to the normal vector. So it generates all of those points. Let's see, what can I do here? What if I vary my P naught, the point that I pick in the plane? So maybe let me bring that, how about I bring x to 0 for that? And so that had the effect of shifting that plane over a bit. Maybe I can shift it even further in the x direction and just keep pushing it along the x-axis like that. So notice I can vary n. That'll change the plane, and I can vary P naught. That'll also change the plane. So let me just do one other thing here. Varying n won't necessarily change the plane, though. So if I pick another vector that's parallel to this one, this n here, so let's say instead of 1, 0, 1, I do 2, 0, 2, all that's done is made my normal vector a bit longer, but it didn't affect the plane at all, right? According to our definition, it shouldn't affect the plane because all the vectors that were once orthogonal to n are still orthogonal to n because the two n's are parallel to each other. I can even send this in the negative direction. I can have the normal vector pointing the other way, and it still generates the exact same plane because, again, it doesn't affect our definition of the plane. All these vectors are still orthogonal to n. So that's something to keep in mind. Also, on the same vein, varying P naught doesn't necessarily change the plane. If I pick another point that's in this plane and choose that for my P naught, again, I'll have the same plane. That's a little bit harder to figure out, so I'm not going to mess with that one of finding another point in the plane. So that's the deal, is we need a normal vector that tells us our orientation of the plane, the collection of all those that are orthogonal or normal to that vector. And then I need just some point in the plane. And together, those give me the rest of the plane. So our mission now is to come up with an analytical expression for all those points in the plane. Again, our starting point is a point in the plane, P naught, that's fixed, and a non-zero normal vector n. It has to have a direction to it, so non-zero. And then, just like we did with lines, we let P be a variable point on the line, and here we'll let P be a variable point in the plane. So I can move P around in the plane. And again, I want my vector equation to spit out all the points that are in the plane by varying some parameter. All right, let's take a look. So what we want to do is we want to collect all vectors that start with P naught and end with P. So all vectors like P naught P that are orthogonal or normal to n. Right, and remember P is a sort of arbitrary point. And that'll be x, y, z. So this P naught P we can actually write analytically because we have these defined. P naught is x naught, y naught, z naught. P is x, y, z. So that means P naught P will look like x minus x naught, y minus y naught. And this is standard procedure, is to put a little subscript of 0 when it's a fixed point, so some subscript if it's fixed, and then no subscript if it's variable. So the x, y, and z, these are our variables for this equation. And x naught, y naught, z naught, these are fixed points. This is just some point in the plane. So I want these to be orthogonal to n. So how do I collect all the orthogonal vectors to this one? Well, remember that u dot v, the dot product of two vectors, is 0 if and only if u and v are perpendicular or orthogonal, or normal. All words meaning the same thing. So what I need is my P naught P vector dotted with my normal vector to give me 0. So we need P naught P dot n to equal 0. If it satisfies this equation, remember P is variable, so x, y, and z. So if this satisfies the equation, a specific x, y, and z that satisfies the equation, that will be a point on the plane, because then this will be an orthogonal vector to the normal vector, and we'll go through the point P naught. So that's the idea. Right, so if x, y, and z are satisfied such that this is true, it's on the plane. And if it's on the plane, then this equation must be satisfied for some particular x, y, and z. So it goes in both directions. And we can actually work out this dot product. Remember, the dot product had a really nice algebraic form, right? You take the product of each of the components and add them all together. So this P naught P dot n, P naught P is this one. So let's maybe go over here. P naught P, x minus x naught. Y minus y naught, z minus z naught, dot my normal vector, which I'm calling ABC. And then we can compute this dot product. We need this to equal 0. We're going to compute it on this side. So what I get is A times x minus x naught plus B times y minus y naught plus C times z minus z naught has to equal 0. So this is one acceptable form for the equation of the plane in terms of x, y, and z. Now there's another form for this that we'll see pretty often. And so what I'll do is I'm going to separate these a little bit. I'm going to write this as ax plus by plus cz equal to, and then, so that's the ax, the by, the cz. When I multiply the a through here, this will be a negative. I'm going to bring that to the other side. So I'll get ax naught plus by naught plus c z naught. And usually we call this, we name this something, we call this d. So another way you can see this equation, so this is also a perfectly acceptable equation of the plane. Or you'll see it just like this. Ax plus by plus cz equal to some constant d, where d is, we have to keep in mind, ax naught plus by naught plus c naught. In other words, it's the dot product of the normal vector with the point that's in the plane. So this is also another way to specify a plane. So notice in this form, this is why we like this one, ax plus by plus cz equals d. This generalizes the notion of lines in 2 dimensions, right? An equation like ax plus by equals c gives me a line in 2 dimensions. It's the general form for a line in 2 dimensions, right? I can solve for y here. If you're not convinced, I'll solve for y here. This is 1 over b times c minus ax, and that gives me what? C over b as my y-intercept minus a over bx. So I have this, y equals this. As long as b isn't 0, this is okay to do, and it generates a function, rather, that gives me a line. So we can see this is the 2-dimensional version, 2D, we get a line. And then if we generalize this equation, we've seen that this gives us a plane. And this is a 3-dimensional object. So again, you can see this generalization from 2 dimensions to 3 dimensions, but the form somehow is staying the same. And this is cool because this allows us to maybe even generalize past 3 dimensions to places that we can't visualize anymore, but still we can have notions of planes and things like this. So I think I will I'll end the video here. In the next video, I'll work through an example of actually finding an equation of a plane given a point and a normal vector. Hope to see you there.